Run your fingers across polished granite in your own kitchen, and you are touching a surface engineered to microscopic tolerances. Now, imagine standing inside an ancient chamber of hard stone, granite, diorite, basalt, and seeing light glide across it in a way that feels uncannily modern. The question is immediate, measurable, and unavoidable. What measurable engineering fact about ancient stone surfaces does not match the assumed technological capability? This is not about mystery. It is not about lost civilizations or impossible machines. It is about numbers. In modern materials engineering, surface finish is not judged by the eye, it is quantified. The standard metric is surface roughness, often expressed as RA, the arithmetic average of microscopic peaks and valleys across a surface. Measured in micrometers, millionths of a meter. A human hair is roughly 70 micrometers thick. A polished industrial granite slab designed for high gloss can reach RA values of 0.2 micrometers or lower. To achieve that, manufacturers use rigid machinery and sequential diamond abrasives, 200 grit, 400 grit, 800, 1500, 3000, sometimes up to 12,000 grit, each stage erasing the microscopic scars left by the one before. Pressure is controlled, the surface is inspected, flatness is verified, reflectivity is measured in gloss units. It is a process chain. Now step into the granite passages of the Great Pyramid of Giza, or examine a diorite statue from the reign of Khafre, its surface dark and luminous. Look closely at certain basalt pavements attributed to the era of Khufu. What you see is not merely smooth. You see high specular reflectivity. Light does not scatter chaotically, it travels. You see stone-to-stone joints so tight that a blade cannot easily enter. You see planes that appear optically true over significant distances. And this is where the contradiction emerges. The contradiction is not that the stone is attractive, not that it was polished. Ancient craftsmen clearly polished stone. There is no debate there. The contradiction is that surface finish is a record of process. It is frozen engineering history. If a granite surface behaves optically like a high-grit, multi-stage polish, then it implies a sequence of abrasion stages, progressively finer control, disciplined inspection, and significant time investment. Modern equivalents demand abrasives harder than the stone itself. Granite and diorite rank around 6 to 7 on the Mohs hardness scale. Copper, the primary metal tool widely available in Old Kingdom Egypt, ranks around 3. Quartz sand, commonly cited as an abrasive, is around 7. It can scratch granite, but scratch is not polish. To move from rough grinding to sub-micron smoothness, the abrasive particles must become progressively finer. Each stage reduces the amplitude of surface peaks. Each stage takes longer than the one before. Fine polishing is exponentially slower than coarse shaping. In modern workshops, this process is measured, calibrated, and often automated. So here is the tension, stated plainly. If ancient finishing methods were limited to copper tools, pounding stones, and sand abrasives, why do some surfaces visually behave like high-grit multi-stage polishing? To answer that, we must understand what we are actually seeing. Reflectivity is not an illusion of color. It is geometry at the microscopic scale. A surface appears glossy when its peaks and valleys are so small that incoming light waves reflect coherently. Diffuse reflection, the matte look, happens when micro-roughness scatters light in multiple directions. Gloss meters quantify this in gloss units. High readings correlate with low RA values. In other words, shine can be measured. Flatness, too, is measurable. A plane that deviates by less than a fraction of a millimeter over a meter will behave differently under light and under straight-edge testing than one that wavers. In modern engineering, granite surface plates used for precision measurement are ground and lapped to tolerances measured in microns. Achieving that requires rigid control of motion and pressure. Random hand abrasion tends to round edges and introduce subtle undulations unless carefully managed. Then there is fit. When two blocks meet with extraordinary tightness, it implies either exceptional shaping precision or compensating techniques. Tight joints are not proof of advanced machinery, but they are evidence of careful control. Surface finish is not decorative fluff, it is mechanical consequence. Consider the diorite statue of Khafra housed in the Egyptian Museum in Cairo. Diorite is notoriously hard, dense, and resistant to abrasion, yet the surface is smooth, subtly reflective. It invites touch. If that finish approaches the equivalent of a fine modern polish, it suggests prolonged abrasion with progressively refined media. It suggests inspection. It suggests a workflow. The assumed technological capability of the Old Kingdom includes copper chisels, dolerite pounding stones, wooden sledges, rope, and sand. These tools are not trivial. With time and organization, they can accomplish extraordinary feats. But there is a difference between capability in principle and documented process in practice. Where is the evidence of sequential grit production, of standardized abrasive grading, of workshops littered with progressively finer polishing residues? Perhaps such evidence exists, overlooked or unpublicized. Perhaps it does not. That gap is what we must explore. We will measure. We will compare ancient surfaces where data is available against modern industrial standards. We will calculate material removal rates. We will examine how long it would take to reduce a granite surface from coarse chisel marks to sub-micron smoothness using sand alone. We will consider the hardness of tools and the mechanics of abrasion. We will model labor time across architectural scale, not merely small artifacts. And we will confront the possibility that what appears anomalous may dissolve under disciplined analysis, or that the anomaly may sharpen. For now, one thing is clear. The eye is a romantic instrument. It is easily seduced by sheen and shadow. Engineering is less forgiving. It demands numbers. Before we can ask how ancient craftsmen achieved what they achieved, before we can speak of contradiction or reconciliation, we must first define, with precision and without sentiment, what smooth actually means. We begin with a discipline older than curiosity and more unforgiving than admiration: measurement. Smoothness is not a poetic quality, it is a number. In engineering, the most common metric for surface texture is RA, the arithmetic average of the absolute deviations from a mean line across a measured length. Imagine dragging a diamond stylus across a surface. As it rises and falls over microscopic peaks and valleys, its vertical movement is recorded. The average of those deviations becomes the RA value. It is expressed in micrometers. 1 micrometer is 1,000th of a millimeter, 1/1,000,000th of a meter. To understand what that means in physical terms, a sheet of ordinary printer paper has a surface roughness on the order of several micrometers. Human skin varies widely, but can measure tens of micrometers depending on location and condition. Precision-machined metal surfaces used in engines may be finished to below 1 micrometer. Optical components, lenses and mirrors, can reach into the nanometer scale. These are not aesthetic categories. They are functional thresholds. At around 5 micrometers Ra, a surface may feel smooth to the touch. The human fingertip cannot reliably distinguish below that range. Yet under magnification, such a surface is mountainous, ridges and troughs large enough to scatter light diffusely. Reduce that roughness to 1 micrometer and the terrain shrinks dramatically. At 0.2 micrometers, the peaks are so subdued that light begins to reflect in a coordinated, specular manner. Gloss emerges not from magic, but from geometry. This is the critical shift. The human eye is not a measuring device. A surface that appears smooth in shadow may still carry 5 micrometers of roughness, 25 times rougher than a highly polished engineered slab. The eye interprets contrast and reflection, not microtopography. Under museum lighting, even a moderately honed stone can appear mirror-like. Without instrumentation, perception deceives. Modern industry distinguishes between ground, honed, and mirror-polished finishes with explicit standards. A ground granite surface is shaped and flattened using coarse abrasives. It retains visible scratch patterns and may measure several micrometers Ra or higher. A honed finish is smoother matte, often used architecturally where reduced glare is desired. Its roughness may range roughly between 1 and 3 micrometers depending on process. A mirror polish undergoes further sequential refinement until the microscopic scratches from previous stages are erased by finer abrasives. The result is low Ra and high gloss. These differences are not subjective, they are confirmed by instruments. A profilometer, mechanical or optical, traces the surface profile and produces a measurable roughness value. Contact profilometers use a diamond stylus with a tip radius small enough to enter microvalleys. Non-contact optical profilometers use interferometry or confocal microscopy, projecting light and analyzing phase shifts to reconstruct three-dimensional surface maps at submicron resolution. Then there is the gloss meter. It emits light at a defined angle and measures the intensity of reflected light at the complementary angle. The result is expressed in gloss units. High gloss correlates with low micro-roughness, though gloss alone does not reveal flatness, only reflectivity at that scale. Flatness itself is measured differently. A surface may have low roughness, yet still be globally warped. Engineers test flatness with precision straight edges, feeler gauges, autocollimators, or laser-based systems. Industrial granite surface plates used in metrology labs are graded according to strict flatness tolerances defined by international standards. These plates are lapped, a slow abrasive process where two surfaces are rubbed together with fine abrasive slurry to achieve deviations measured in micrometers across entire meters of length. It is important to separate three ideas that are often conflated: smoothness, gloss, and flatness. Smoothness concerns micro-scale roughness. Gloss concerns optical behavior resulting from that roughness. Flatness concerns macro-scale geometric accuracy. A stone surface may be smooth but not flat, flat but not glossy, glossy but subtly warped. Industrial granite slabs used in kitchens are not optical components. They are polished for appearance and stain resistance. Their Ra values can drop below 1 micrometer, sometimes below half a micrometer, depending on finishing standards. Optical grade surfaces, telescope mirrors, precision reference flats demand far lower irregularities. There, deviations are measured in nanometers, thousands of times smaller than architectural polish. Achieving that requires extraordinary control and long-duration lapping and polishing cycles. Architectural standards sit between these extremes. They require aesthetic gloss, durability, and relatively uniform surface texture. They do not demand the perfection of optical physics, but they do require consistent, sequential abrasion. This establishes the benchmark. If a surface is measured at 5 micrometers Ra, it is relatively coarse in engineering terms, even if it feels smooth. At 1 micrometer, it is finely finished. At 0.2 micrometers, it approaches high-grade architectural polish. Below that, one enters specialized territory. Why does this matter? Because every reduction in Ra demands disproportionate effort. Coarse grinding removes material quickly. Fine polishing removes material slowly. The finer the target finish, the more sensitive the process becomes to pressure, abrasive size distribution, slurry consistency, and surface inspection. Micro peaks must be uniformly reduced. Random pressure leads to unevenness. Over-polishing one area introduces curvature. Under-polishing leaves residual scratches that scatter light. Surface finish is therefore evidence of process control. It implies awareness, whether explicit or intuitive, of stages. One does not stumble accidentally into a consistent 0.5 micrometer finish across broad areas without some form of systematic repetition. And so the benchmark is set. We know what modern industrial granite looks like under measurement. We know how honed and polished finishes differ numerically. We understand how gloss meters and profilometers quantify what the eye cannot. The question now sharpens. When ancient granite, basalt, or diorite surfaces are examined, when light glides across them and reflections appear coherent, what do the numbers say? Are we observing finishes equivalent to honed surfaces at several micrometers? Or do some approach the lower ranges associated with deliberate high-grit polishing? If we place a profilometer upon those ancient plains, where would the stylus rise and fall? How high are the microscopic mountains? How deep the valleys? In other words, if we measure ancient surfaces, where do they fall? What do you think about this? Do share with us in the comments section. Stand before a block of dark stone in a museum gallery and watch what happens when light moves across it. If the surface is coarse, the light fractures. It scatters in 1,000 directions, breaking into a soft haze. Edges blur. Highlights dissolve. The stone appears matte, almost absorbent. But when the surface is refined, truly refined, something else occurs. A window frame reflects clearly. A lamp forms a crisp band of brightness. The room itself becomes visible in the stone. Light no longer scatters chaotically, it behaves. This is the threshold where aesthetics give way to physics. Reflectivity is not a matter of color. It is not the inherent darkness of diorite or the mineral composition of basalt that produces a mirror-like gleam. It is geometry at a scale too small for the naked eye. When a beam of light strikes a surface, its behavior depends entirely on the orientation of microscopic peaks and valleys. If those microfeatures vary wildly in angle, incoming light rays are redirected unpredictably. The result is diffuse reflection, the matte appearance familiar in unpolished rock. If, however, the microtopography becomes sufficiently subdued, if the peaks are lowered and the valleys filled through abrasion until their scale approaches fractions of a micrometer, then the incoming rays encounter a surface whose deviations are smaller than the wavelength of visible light. Under those conditions, reflection becomes specular. Light leaves the surface at a predictable angle, maintaining coherence. The surface begins to act like a mirror. This is not metaphor, it is measurable wave interaction. Visible light has wavelengths roughly between 0.4 and 0.7 micrometers. When surface irregularities are significantly larger than that range, scattering dominates. When irregularities fall below or near that range, coherent reflection increases dramatically. That is why mirror behavior requires sub-micron control. The geometry of the surface must be disciplined to a scale comparable to the light itself. Now consider the diorite statues from the Old Kingdom of Egypt. Dense, dark stone carved with remarkable precision. The seated figure of Khafra is often cited, but he is not alone. Numerous basalt vessels and granite sarcophagi exhibit surfaces that appear, under controlled lighting, to reflect with a consistency that feels almost modern. Highlights travel across the contours rather than dissolving into grain. This behavior implies something very specific. To move from a rough-hewn stone surface to one that reflects specularly, abrasion must pass through successive thresholds. Coarse pounding or chiseling leaves deep micro-grooves. Sand abrasion reduces these but introduces its own patterning depending on grain size. To remove the scratches created by one abrasive, a finer abrasive must follow. Each stage reduces the amplitude of surface irregularities. Each stage narrows the distribution of micro-angles across the surface. Specular reflection is therefore a cumulative achievement. It is the geometric consequence of progressive refinement. Basalt provides a particularly revealing case. It is fine-grained and dark, which makes reflectivity visually dramatic. When polished, basalt can achieve high gloss, but basalt is also hard and dense. Its mineral structure resists rapid abrasion. To produce coherent reflectivity across broad surfaces requires sustained, controlled polishing. It is not enough to shape the form. The surface must be disciplined at the microscopic level. And here is the essential point. Reflectivity is not decorative. It is geometric. A glossy surface announces the scale of its own microtopography. It tells us without sentiment that its peaks and valleys have been reduced below certain thresholds. It signals that scratch patterns from previous abrasion stages have been erased by finer media. It implies time, repetition, and inspection. This is why engineers use reflectivity as an indirect gauge of surface quality. While gloss meters provide numerical values in gloss units, the physics behind the reading is always the same. Smoother surfaces reflect more coherently. Rougher surfaces scatter. But reflectivity alone can deceive if interpreted casually. A curved surface can reflect sharply even if it is not flat. A statue's cheek may appear mirror-like because it has been polished to low micro-roughness, yet that tells us nothing about whether the broader plane of a stone block is geometrically true. Reflectivity reveals micro-smoothness. It does not confirm macro-precision. Still, its implications are profound. When we observe specular behavior on ancient diorite or basalt artifacts, we are not merely admiring craftsmanship. We are witnessing the physical consequence of surface reduction to scales approaching the wavelength of light. That achievement requires abrasives of sufficient hardness and fineness. It requires controlled pressure to avoid introducing new scratches. It requires awareness, even if intuitive rather than theoretical, that refinement must proceed in stages. It also raises a practical question of scale. Polishing a small ceremonial vessel to a reflective sheen is one thing. Polishing the interior walls of a granite chamber or the surface of a large sarcophagus is another entirely. The larger the surface area, the more uniform the microtopography must be to maintain consistent reflection. Uneven polishing produces patchy gloss, areas of higher scatter, visible transitions. When reflectivity appears uniform across large stone surfaces, it implies sustained, evenly distributed abrasion. It implies not only effort, but method. This is where the inquiry deepens. If reflectivity correlates directly with microsmoothness, and if microsmoothness requires sequential abrasive refinement, then the presence of coherent reflection in ancient stone suggests a process that extended beyond simple shaping. It suggests finishing stages that reduced roughness to very fine scales. It suggests time invested not merely in carving, but in surface discipline. Yet we must remain cautious. Light can flatter. Museum conditions can exaggerate gloss. Dark stone inherently enhances contrast, making highlights appear sharper. Without instrument readings, reflectivity remains an optical clue, not a final verdict. Nevertheless, it marks a threshold in our investigation. Specular behavior tells us that micro-roughness has been controlled to a degree that interacts coherently with visible light. It signals submicron geometry. It implies a process chain capable of reducing surface deviations into ranges typically associated with deliberate fine polishing. And yet, reflectivity speaks only of the microscopic terrain. A surface may gleam beautifully while still deviating subtly from a true plane over larger distances. It may reflect sharply while harboring gentle undulations invisible to the eye but measurable with a straight edge, which leads us to the next problem. If a surface shines like a mirror, does that mean it is geometrically true? Reflectivity reveals micro-smoothness. But reflectivity alone does not prove flatness. A surface can shine like still water and yet be warped like a bow. This is the plane problem. Reflectivity tells us about micro-smoothness, the scale of peaks and valleys measured in micrometers. But flatness operates at a different scale entirely. It concerns the macro-geometry of a surface across centimeters, across meters. It asks not whether the microscopic terrain is subdued, but whether the entire plane lies in disciplined alignment. And flatness is mercilessly measurable. The simplest test is ancient in concept and modern in precision, the straight edge. Lay a precision ground bar across a stone surface and hold it to the light. If light bleeds through at certain points, there is deviation. Engineers refine this with feeler gauges, thin, calibrated strips inserted into gaps to quantify the separation in fractions of a millimeter. In machine shops, granite surface plates are certified to specific flatness grades. Deviations are mapped across grids, measured at dozens or hundreds of points. But contemporary industry has gone further. Laser flatness measurement projects beams across surfaces and detects variations by analyzing reflected angles. Autocollimators measure minute angular deviations across planes. And then there is interferometry, perhaps the most unforgiving method of all. In optical interferometry, coherent light waves are reflected from a reference surface and the test surface simultaneously. When recombined, they produce interference patterns. Each fringe corresponds to a fraction of a wavelength of light. Deviations of mere nanometers become visible as shifts in pattern. In such systems, flatness is not estimated, it is revealed in waves. These tools allow modern engineers to certify granite reference plates to tolerances of a few micrometers across entire meters of span. In optical manufacturing, even tighter tolerances are routine. Why does this matter in stone? Because flatness is not an aesthetic flourish. It is a geometric achievement that requires directional control during abrasion. When a surface is randomly sanded by hand without a consistent motion, the natural human tendency is to create slight convexity. The wrist pivots, pressure varies. High spots are reduced, but valleys may deepen unevenly. Over time, unless carefully checked, the surface subtly curves. True planar flatness requires controlled abrasion direction. It requires systematic coverage. It often requires using one flat surface to grind against another, a method known as lapping, so that both converge toward mutual flatness. Without such feedback, achieving a uniformly flat plane across a large block becomes increasingly difficult as the target tolerance tightens. Now, consider tightly fitted granite blocks from the Old Kingdom. Joints where two stones meet with astonishing intimacy. The casing stones once sheathing the Great Pyramid of Giza were described by early surveyors as exhibiting extremely fine jointing. The internal granite blocks in certain chambers appear to meet with minimal visible gap. The basalt pavement fragments near the pyramid complex, attributed to the era of Khufu, show broad, smooth upper surfaces that suggest intentional planarity. When two flat planes meet with tight tolerance, several things must be true. First, each individual plane must be sufficiently flat. Second, their orientation relative to one another must be controlled. Third, high spots must have been identified and reduced selectively. This implies inspection. It implies iteration. Flatness tolerances in engineering are defined relative to length. A deviation of 0.1 millimeters across 10 centimeters may be trivial. The same deviation across 2 meters may represent notable precision. As scale increases, maintaining proportional flatness becomes exponentially demanding. Minor angular errors accumulate. Abrasive pressure must be distributed evenly. This is where the investigation deepens. Microsmoothness can be achieved on a curved surface. A statue's cheek can gleam without being geometrically flat. But architectural planes, large load-bearing stone surfaces, introduce a different challenge. If ancient granite surfaces were polished not only to reflect light coherently, but also to maintain planar truth across significant spans, then the process required more than persistence. It required method. Random sanding does not produce planar truth. To produce a plane, abrasion must be either constrained or guided. One method involves marking high spots with pigment, abrading selectively, reapplying the marker, and repeating. Another involves rubbing two stones together with abrasive slurry, allowing high points to wear preferentially. Both methods are conceptually simple. Both demand time and discipline. Neither demands steel machinery, but both demand awareness that flatness is being pursued intentionally. If we observe tightly fitted joints between granite blocks, we must ask, were they shaped independently and simply happened to match? Or were they test-fitted repeatedly, high points shaved away through trial and correction? The latter implies a workflow approaching what modern engineers would recognize as iterative surface refinement. Yet caution is essential. Apparent tight joints may conceal small irregularities invisible at casual glance. Lighting conditions, shadow, and erosion over millennia complicate interpretation. Without systematic measurement using modern instruments, visual assessment alone cannot confirm micron-level flatness. Still, the existence of extensive smooth planes in hard stone, especially when combined with tight fit, suggests directional abrasion and inspection. It suggests that surfaces were not merely rubbed until pleasing, but worked until conforming to some functional requirement, whether aesthetic, structural, or symbolic. Flatness, like reflectivity, is a silent testimony to process. It records whether abrasion was chaotic or disciplined. It reveals whether surfaces were allowed to wander into curvature or corrected back into plane. And here lies the pressing question. Even with copper tools, sand abrasives, and patient labor, could simple abrasion and time alone produce consistent planar accuracy across large granite surfaces? Could repeated manual grinding, guided by sight and touch alone, converge toward tolerances that appear striking even today? Or does the evidence imply something more organized, not technologically advanced in the modern sense, but procedurally sophisticated? We are now standing between perception and physics. Reflectivity told us about microscale discipline. Flatness demands macro-scale control. Together, they begin to form a portrait of process. But before drawing conclusions, we must confront the fundamental variable underlying both smoothness and flatness. How fast does hard stone actually yield under abrasion, and how much time would it truly take? Stone does not care about intention. It responds only to physics. To understand whether ancient surfaces represent a contradiction or a triumph of patience, we must examine the fundamental battlefield, hardness. Because polishing is not magic, it is abrasion, and abrasion is governed by relative hardness, fracture mechanics, and grit geometry. Granite, basalt, and diorite are not soft materials. Granite is an igneous composite rock composed primarily of quartz, feldspar, and mica. Quartz is the critical player. On the Mohs scale of mineral hardness, quartz ranks at 7. Feldspar typically falls around 6. Diorite contains similar silicate minerals and often significant quartz content. Basalt contains less quartz but still includes hard silicates, typically ranging between 6 and 7 in hardness depending on composition. These numbers matter because abrasion follows a simple rule. The abrasive must be at least as hard as, and preferably harder than, the material being cut. Copper, the often cited tool material of Old Kingdom Egypt, has a Mohs hardness of approximately 3. It is dramatically softer than granite or diorite. A copper edge cannot meaningfully cut quartz-rich stone by itself. Under pressure, copper deforms long before quartz fractures. So how were hard stones shaped? The answer is abrasives. Quartz sand, abundant in Egypt, also ranks at 7 on the Mohs scale. When trapped between a copper tool and stone surface, quartz particles can act as cutting agents. The copper serves as a carrier or matrix. The sand performs the cutting. This is not hypothetical. Abrasive slurry cutting is well documented in experimental archaeology. When quartz grains are forced across granite under pressure, they fracture microchips from the surface. Each grain acts like a tiny plow. But polishing is not just cutting, it is refinement. Surface smoothness improves as the abrasive grit becomes progressively finer. Large particles remove material quickly, but leave deep scratches. Smaller particles remove less material per pass, but create shallower grooves. Modern granite polishing follows a strict sequence: coarse diamond segments, perhaps 50 to 100 grit, then 200, 400, 800, 1,500, 3,000 grit, sometimes progressing beyond 8,000 or even 12,000 grit for mirror finishes. Why diamond? Because diamond ranks at 10 on the Mohs scale, the hardest known natural material. It cuts quartz effortlessly. Modern polishing pads embed industrial diamond particles into resin or metal matrices. Under controlled pressure and rotation, these abrasives shear microscopic peaks away with predictable efficiency. Submicron smoothness, RA values below 0.2 micrometers, generally requires abrasive particles measured in only a few micrometers in diameter. At that scale, each particle removes extremely small amounts of material, smoothing peaks without introducing deep new scratches. This brings us to a crucial question. What grit sizes would be required to produce a surface approaching optical smoothness on granite? A rough equivalence used in finishing industries correlates grit size to surface roughness. A 400 grit abrasive might leave scratch depths measurable in several micrometers. To approach submicron smoothness, abrasives in the thousands of grit range are typically required. These correspond to particle sizes of perhaps 5 micrometers or smaller. Natural quartz sand varies widely in grain size. Desert sand often contains rounded grains, but typical grain diameters can range from tens to hundreds of micrometers. Such grains are effective for shaping and smoothing to moderate levels, but achieving a true mirror-like polish requires extremely fine abrasive fractions. Could ancient workers have produced fine quartz powder? Mechanically, yes. Crushing and sieving sand could separate smaller fractions. Grinding quartz against itself produces progressively finer particles as grains fracture. However, the distribution would not be as tightly controlled as modern industrial grading, where particle size tolerances are precisely specified. Still, physics does not forbid the existence of fine abrasives in antiquity. It only imposes consequences. As abrasive particles become smaller, the material removal rate decreases dramatically. Each grain carries less kinetic energy and removes less volume per pass. Polishing transitions from shaping to burnishing. Time increases exponentially as target smoothness decreases. This is the trade-off. Modern systems compensate by increasing pressure, optimizing contact geometry, and using rigid machines to maintain uniform motion. Copper hand tools, by contrast, deform. They distribute pressure unevenly. Human-applied force fluctuates. Abrasive slurry may migrate unpredictably across the surface. Tool hardness also influences geometry control. A soft copper plate holding abrasive can conform slightly to the stone's contour. This can be advantageous for smoothing curves, but problematic for maintaining flatness. A rigid cast iron lap, as used historically in optical grinding, preserves plane geometry more reliably. Basalt and diorite present additional complexity. Diorite, composed of interlocking crystals, often has a heterogeneous microstructure. Polishing such a surface evenly requires that abrasives cut multiple mineral phases at similar rates. If one mineral resists more strongly, microtopography can develop at grain boundaries. Basalt, being fine-grained, may polish more uniformly, but its hardness still challenges soft tool matrices. So we stand at a physical crossroads. Copper cannot cut granite alone. Quartz sand can. Finer quartz can refine. Diamond makes it efficient, but diamond is not required in principle. The real question is not whether polishing hard stone is possible with quartz abrasives. It is demonstrably possible. The question is efficiency. To reduce granite surface roughness from visible scratch depths down to submicron smoothness using only quartz slurry and hand-applied pressure would demand sequential abrasive refinement and substantial time investment. It would require awareness that progressively finer material is needed. It would require maintaining uniform pressure and motion over long durations. This is where the contradiction, if one exists, must reside, not in impossibility, but in scale. Because even if the necessary abrasives were available, how long would it actually take to achieve that finish? Polishing is not an act. It is an ordeal. To understand whether ancient stone finishing represents a contradiction, we must move from theory to arithmetic. Hardness tells us what is possible. Time tells us what is plausible. Let us begin with surface area. Imagine a granite block face measuring 1 meter by 1 meter. That is a single square meter, modest by architectural standards. Many casing stones at the Great Pyramid of Giza exceeded this dimension. Interior granite beams in the King's Chamber are larger still. Basalt pavements near the pyramid complex covered many square meters. But start small. 1 square meter equals 10,000 square centimeters. Every square centimeter must be abraded repeatedly through multiple grit stages if a high polish is the goal. Now consider material removal rate. In modern industrial granite, grinding using diamond tooling under powered rotation, coarse grinding might remove on the order of millimeters per hour across broad surfaces. But that is with kilowatts of mechanical energy and abrasives harder than quartz. With hand-applied quartz slurry and copper tools, removal rates drop dramatically. Experimental archaeology and lapidary studies suggest that shaping granite with quartz sand and manual force may remove material on the order of fractions of a millimeter per hour per worker, and that is during coarse shaping, where grit sizes are large and removal is aggressive. Fine polishing is a different regime entirely. As grit size decreases, material removal rate declines non-linearly. Each abrasive particle becomes smaller, carries less force, and removes less volume per pass. Scratches become shallower, but progress slows. Let us model this conceptually. Suppose coarse grinding removes 0.5 millimeters of surface height variation in 1 hour across a given patch under sustained effort. To reduce scratch depth from, say, 100 micrometers to 10 micrometers might require several hours with mid-grade abrasive. To then reduce from 10 micrometers to 1 micrometer could take significantly longer. To push below 1 micrometer towards sub-micron smoothness may require hours more per small area, not because stone resists, but because the peaks being removed are microscopic. Polishing operates under diminishing returns. Each stage only removes the damage introduced by the previous stage. If a coarse grit leaves scratches 50 micrometers deep, the next finer grit must remove at least that depth uniformly before its own finer scratch pattern dominates. This creates a staircase of time investment. Now apply this to area. If one worker can effectively polish with fine grit, perhaps 100 square centimeters per hour to a near-finished stage, and that is generous under hand conditions, then polishing 1 square meter, 10,000 square centimeters, would require 100 hours for that stage alone. And that is one stage. Modern granite polishing often involves at least 6 or more grit progressions beyond initial shaping. Even if ancient workers used fewer distinct grades, a transition from coarse sand to progressively crushed finer quartz would still imply multiple passes. Let us imagine a simplified sequence: coarse grind, medium grind, fine grind, very fine polish, 4 stages. If each stage requires conservatively 80 to 100 labor hours per square meter to achieve uniform coverage and remove previous scratches, we approach 320 to 400 labor hours per square meter. This is not impossible. It is simply large. Now consider pressure limitations. A human applying downward force through a copper plate or stone rubbing block can exert perhaps 100 to 200 newtons comfortably for sustained periods. Industrial machines apply far more and do so continuously without fatigue. Human force fluctuates, arms tire, pressure distribution shifts, efficiency decreases over long sessions. Moreover, slurry-based abrasion wastes motion. Abrasive particles roll and migrate. Only a fraction of applied force contributes to cutting at any moment. In modern lapping systems, abrasive is embedded or constrained to increase efficiency. Hand polishing is energetically inefficient. Next, consider geometry. Maintaining uniform abrasion across an entire square meter requires systematic coverage. If pressure concentrates in one area, low spots develop. To avoid curvature, workers must sweep in overlapping patterns, likely repeatedly crossing directions to average out bias. This multiplies motion. Now, scale up psychologically. 400 labor hours per square meter means 10 full 40-hour work weeks for one individual, for one surface, for one finishing level. If a block has multiple exposed faces requiring similar finish, time multiplies accordingly. If a project contains dozens of such surfaces, labor scales into thousands of hours. At this point, one might argue, ancient societies had large labor forces, time was abundant. Monumental architecture is itself proof of vast labor investment. That is true. But polishing differs from stacking blocks. It is sequential. It requires trained hands. It requires patience and consistency. It cannot be rushed by brute manpower alone. 10 workers cannot easily polish the same square meter simultaneously without interfering with one another's geometry control. The process does not parallelize efficiently at small scales. The key principle emerges: fine polishing is exponentially slower than coarse grinding. Coarse abrasion attacks millimeters, fine polishing shaves microns. The last 10% of surface refinement may consume more time than the first 90%. Now add iteration. If flatness is being pursued alongside smoothness, surfaces may require repeated inspection and correction. High spots identified through fitting against adjacent stones must be abraded selectively. This introduces localized rework that can cascade backward into earlier grit stages if deep corrections are needed. Every correction costs time, yet time alone does not invalidate feasibility. Ancient craftsmen could invest extraordinary labor in elite objects. Consider the diorite statue of Khafra. Its polished surfaces demonstrate that hard stone finishing was within their capability. Smaller artifacts clearly received extensive finishing effort. But we are now approaching the tension.
What happens when the surface area is not a statue's cheek, but architectural?
When instead of a few hundred square centimeters, we confront tens of square meters of granite flooring. When instead of one block, we observe entire chambers lined with smooth surfaces. At that scale, polishing transitions from artisanal detail to industrial process. Labor hours accumulate into tens of thousands. Workforce coordination becomes necessary. Abrasive supply must be continuous. Water for slurry must be transported. Grit must be graded or progressively refined. Surfaces must be inspected systematically. The ordeal becomes organizational, not merely physical, so the question sharpens: could time and human effort alone, under the constraints of copper tools and quartz abrasives, reasonably account for the extent of high-finish hard stone surfaces observed in certain ancient contexts? Or does the apparent quality imply a level of process control and perhaps production efficiency that exceeds what simple hand abrasion models predict? Before answering, we must enlarge the frame even further. Because a polished artifact is one thing, a polished architectural complex is another entirely. What happens when the surface area isn't small but monumental? There is a profound difference between polishing an object you can cradle in your arms and refining a structure that weighs 70 tons. Scale changes everything. A small artifact, a diorite bowl, a statue, a ceremonial mace head, can absorb immense labor. Its surface area is limited, its geometry is manageable. A skilled craftsperson can rotate it, inspect it from all angles, and devote weeks or months to refinement. Architecture does not behave that way. Consider the massive granite sarcophagi in the Serapeum at Saqqara. These boxes, often weighing more than 60 tons, possess interior surfaces that appear remarkably smooth. The internal chambers of these boxes measure several meters in length and over a meter in height and width. The total interior surface area easily reaches 10 to 15 square meters per sarcophagus. Now recall the earlier time model. If fine polishing 1 square meter requires several hundred labor hours across sequential abrasive stages, then polishing 10 square meters could demand thousands of hours per box. And there are more than 20 such sarcophagi in the complex. Even if our estimates are halved, the cumulative labor required becomes immense. The same scaling problem appears in the granite columns and architraves of the New Kingdom. Massive cylindrical columns, some carved from single granite drums, exhibit smooth surfaces across their curvature. The exposed surface area of one large column can exceed 15 square meters. Achieving uniform smoothness across a convex cylindrical geometry adds further difficulty. Unlike a flat slab resting horizontally, a column's curvature requires controlled motion along arcs while maintaining even pressure. Then there are basalt pavements. Near the pyramid complex at Giza lie fragments of a black basalt floor, traditionally attributed to the era of Khafra. These pavement stones are large, thick slabs with broad upper surfaces that appear intentionally leveled and smoothed. Some reconstructions estimate the original paved area covered hundreds of square meters. Even if only a fraction of that area was finished to high smoothness, the labor implication multiplies dramatically. Small artifact polishing is one thing, multi-ton architecture is another. When scale increases, three pressures emerge simultaneously. Surface area multiplies, inspection complexity increases, logistical overhead expands. First, surface area. A single statue head might require 50 square centimeters of high polish. A sarcophagus interior might require 100 times that. A pavement could require 1,000 times that. Because polishing time scales roughly with area, the total labor requirement scales linearly, but the organizational burden scales non-linearly. Second, inspection complexity. On a small object, high spots can be felt by hand. The eye can scan the entire piece at once. On a 3-meter interior chamber, maintaining uniform smoothness demands systematic mapping. Workers must move inside confined spaces, applying abrasive in constrained positions. Lighting becomes critical. Variations in geometry become harder to detect without consistent reference tools. Third, logistics. Abrasive slurry must be mixed continuously. Water must be transported. Spent grit must be cleared. Copper tools must be maintained or reshaped. Workers must rotate to avoid fatigue. The process becomes not just labor-intensive, but administratively intensive. This is the scale problem. One might respond that ancient Egypt possessed extraordinary manpower. During the construction of the Great Pyramid of Giza, thousands of workers were organized seasonally. Quarrying, transport, and placement of stone blocks required coordination at scale. True. But polishing does not parallelize as easily as hauling blocks. 10 workers cannot efficiently polish the same square meter simultaneously. They would interfere with one another's pressure control and motion patterns. Fine finishing tends to be sequential and spatially constrained. However, work can be distributed across surfaces. One team polishes one slab, while another works on a different slab. That spreads effort, but it also multiplies abrasive demand and supervisory oversight. To evaluate plausibility, we must imagine a realistic labor model. Suppose a team of 20 skilled finishers is assigned to granite polishing tasks. If each worker contributes 1,500 effective labor hours per year, accounting for rest, festivals, agricultural seasons, the team produces 30,000 labor hours annually. If polishing a single large sarcophagus interior demands conservatively 4,000 to 5,000 labor hours, that team could complete perhaps 6 or 7 per year, assuming no other finishing duties. This suggests that even monumental polishing tasks are not outside the realm of possibility for a centralized state with resources and time. Yet another factor complicates the analysis: consistency. If large-scale polished surfaces appear uniform in quality across multiple monuments and generations, that implies institutional knowledge. It implies standardized technique. It implies training systems capable of reproducing finish levels predictably. Polishing at architectural scale becomes less about brute endurance and more about process control. It is here that the psychological weight of scale becomes evident. A craftsman polishing a ceremonial object can focus entirely on that object. A state-level project polishing hundreds of square meters of granite must coordinate schedules, resource flow, and quality control. the margin for inefficiency becomes enormous. Still, none of this proves impossibility. It only reveals magnitude. The scale problem does not argue that ancient polishing could not have occurred. It asks whether the documented technological toolkit, copper implements, quartz abrasives, hand pressure, aligns with the observed extent of finished hard stone surfaces when time and organization are modeled realistically. And this leads to the next critical question. If scale increases time dramatically and if fine polishing consumes disproportionate labor, did the civilization in question possess not merely manpower, but the sustained labor capacity and administrative discipline to absorb such an undertaking repeatedly? Because polishing a single monument is impressive, polishing across an architectural tradition is transformative. Diorite is the stone of paradox. Dense, coarse-grained and extraordinarily hard, it resists not only chisels but intuition. Its mineral composition, interlocking crystals of feldspar and quartz, makes it one of the most challenging materials a sculptor can choose. Basalt, by contrast, is fine-grained, homogeneous and dark, but it too is unforgiving, resisting abrasion and revealing every imperfection through reflected light. Both stones have survived millennia, and both carry silent testimony. Their surfaces suggest deliberate, laborious finishing that challenges assumptions about ancient technology. Archaeologists and lapidary specialists have long marveled at diorite artifacts from the Old Kingdom. The famous statues of Khafra, carved from diorite, present surfaces that reflect light in a manner reminiscent of modern polished stone. Every plane appears controlled, every curve follows a subtle geometric discipline. The contrast between the raw stone beneath and the finished surface is stark. Deep scratches from initial shaping are almost entirely absent. Where one might expect residual marks from hammering or chisel work, there is instead smooth, continuous transition across angles. The surface is coherent in microtopography, suggesting sequential refinement with a knowledge of abrasion progression, even if unspoken or intuitive. Basalt presents a different puzzle. As a volcanic rock, it is dense, brittle and fine-grained, often forming sheets for architectural use. Pavement stones discovered near pyramid complexes show polished upper surfaces, flat within millimeter tolerances over several meters. Unlike small artifacts, these stones were functional as flooring. They had to endure foot traffic, yet exhibit uniform gloss across broad spans. The challenge of producing a reflective surface on basalt lies not in the creation of shine alone, but in doing so without introducing micro cracks or uneven polishing patterns. Unlike diorite statues, which could be rotated and held, these stones had fixed orientation. Achieving uniformity required consistent pressure, systematic abrasion, and repeated verification. Experimental reconstructions offer some insight. Researchers have attempted to replicate diorite finishing using copper tools with quartz sand abrasives. Initial coarse grinding produces rapid removal of high spots, but micro scratches remain. Finer abrasives reduce roughness incrementally. Observations show that achieving a visually coherent, mirror-like sheen demands extreme labor investment. Small test blocks can reach impressive finish after weeks of continuous effort, yet the process is painstaking and unforgiving. Fatigue, uneven pressure, and inconsistent abrasive quality create patchiness. Only through iterative feedback, inspecting the surface, removing high points and refining, does a surface approach the level of coherence observed in archaeological artifacts. In these experiments, abrasive grain size is critical. Large sand grains remove material efficiently but leave deep scratch marks. Medium grains smooth these marks but cannot erase them completely. Very fine fractions, often below 20 micrometers, are necessary to reduce roughness towards sub-micron levels. Each transition consumes substantial time, and efficiency declines sharply as grit becomes finer. Even with careful technique, producing a sub-micron finish across a surface of even a few hundred square centimeters takes weeks for a single craftsman. Multiply that across meters of diorite or basalt, and the labor requirement becomes staggering. Basalt experiments highlight another constraint: pressure distribution. Uneven force produces localized gouging or uneven gloss. Polishing large slabs requires sustained, evenly applied pressure. The natural deformation of copper tools under force limits consistency. Experimental results show that workers must adjust technique, sometimes using auxiliary devices to distribute load. The simplest method, rubbing a flat stone against another with slurry, can achieve partial polish, but only meticulous iteration yields uniform reflectivity. The process reveals that while hardness can be overcome, scale imposes exponentially increasing difficulty. Comparing experimental surfaces to archaeological examples reveals gaps. Test blocks rarely reach the same combination of uniform flatness, sub-micron smoothness, and coherent reflectivity over broad spans. Small areas can approximate the effect, but the larger the surface, the harder it becomes to maintain consistency. Diorite statues in museums show mirror-like reflection across several decimeters. Basalt floors maintain flatness and gloss across square meters. Experiments produce promising analogues on small scales, but rarely reproduce the same level of finish when extended to architectural dimensions. The evidence suggests that ancient craftsmen possessed sophisticated understanding of the interplay between abrasives, pressure, and iteration. Even if methods were slow and labor-intensive, the outcomes demonstrate intentionality and procedural awareness. Repetition, inspection, and progressive refinement were likely integrated into their workflow, even if no formal documentation exists. This is not a question of advanced technology in the modern sense, but of disciplined, cumulative process. At the same time, the experiments underscore the contradiction we have been tracing. Achieving the observed quality on small artifacts is within the realm of possibility given time, labor, and method. Scaling this up to sarcophagi interiors, columns, and basalt pavements introduces compounding challenges. Labor estimates, abrasive preparation, force control, and inspection cycles multiply. Every incremental increase in surface area amplifies the physical and organizational demands. The task is not impossible, yet the precision and uniformity of finished surfaces invite scrutiny. Could such outcomes be consistently achieved across multiple monuments and centuries, using only hand-applied copper tools and sand, without more systematic workflow organization than simple craft tradition? Ancient diorite and basalt provide tangible test cases for our inquiry. They embody both the physical properties of extremely hard rock and the visual evidence of micro-smooth, reflective, and planar surfaces. They allow experimental archaeology to explore the limits of possibility and highlight the tension between what is physically achievable and what appears to have been realized. They demand detailed measurement, raw values, gloss units, flatness tolerances. They invite modeling of labor input and abrasive efficiency. In short, they sit at the intersection of measurable engineering fact and assumed technological capability. What remains to be seen is whether experimental reconstructions, when scaled realistically in labor and method, can fully reproduce the surface qualities recorded in the archaeological record. This question will guide the next stage of analysis, where time, workforce, and technique converge to challenge our assumptions about ancient mastery of stone. Modern experimental archaeology has approached ancient stone finishing with a mix of reverence and skepticism. Teams across the globe have sought to recreate the surfaces we see in museums and archaeological sites, using only materials and techniques plausibly available to ancient craftsmen: copper tools, quartz abrasives, and human labor. The objective is not to conjure lost magic, but to measure, quantify, and confront the question at the heart of our investigation. Can these techniques produce the measurable surface qualities we observe in diorite, granite, and basalt artifacts? The experiments begin with basic principles. Researchers select blocks of hard stone, often granite or diorite, roughly comparable in grain size and composition to ancient examples. Copper chisels or plates serve as the primary contact tool. quartz sand is crushed into multiple size fractions, from coarse grains for initial shaping down to the finest powders obtainable with hand mortars and sieves. Water is added to create a slurry, enhancing abrasive efficiency and reducing heat. Initial results confirm what physics predicts: coarse shaping is feasible. Copper tools, guided by abrasive, can remove millimeters of surface height in a few hours, particularly when the abrasive is coarse. High spots fracture preferentially, and rough contours gradually emerge. The visible scratches are deep, but uniformity across small patches is achievable with consistent motion. These early stages align well with archaeological evidence of tool marks on partially finished diorite bowls or basalt slabs. The challenge emerges during fine polishing. Teams attempt to reduce surface roughness from tens of micrometers down to levels approaching optical smoothness, sub-micron or RA, less than or equal to 0.2 micrometers. Here, the limits of period-accurate techniques become starkly apparent. Coarse quartz grains no longer suffice. Finer grains are needed, but producing and handling sub-20 micrometer particles with hand mortars is slow and inconsistent. Abrasive distribution is uneven. Copper plates deform under pressure, concentrating force in some regions while leaving other areas under-abraded. The human factor, fatigue, slight variation in hand movement, and imperfect surface contact introduces irregularities that accumulate. Measurements of reproduced surfaces provide a quantifiable insight into the contradiction. Profilometers used in modern labs reveal that hand-polished surfaces often achieve Ra values between 1 to 5 micrometers after extended effort. They are visibly smoother than rough-hewn stone, but they do not match the sub-micron smoothness or optical coherence observed in archaeological diorite statues or granite sarcophagi interiors. Gloss measurements expressed in gloss units indicate reflective behavior that is perceptibly muted. Microtopography remains inconsistent. Tiny scratches, unevenness, and subtle undulations are always present. Even scaling back expectations to small artifact-sized blocks demonstrates the labor intensity. A 20-centimeter square diorite test block requires dozens of hours at fine abrasive stages to approach Ra approximately 1 micrometer, far above the 0.2 micrometer typical of highly polished ancient artifacts. Effort scales rapidly with surface area. Extending these methods to a sarcophagus interior of several square meters or a granite floor slab becomes daunting. Time estimates reach thousands of labor hours per surface, assuming perfect continuity, fatigue-free workers, and continuous supply of progressively finer abrasive. Minor deviations in any parameter amplify errors, requiring iterative correction and further labor. Some experimental teams introduce controlled improvisations to observe limits. Copper plates are reinforced or weighted to increase pressure stability. Abrasive slurry is sieved to remove coarse particles. Surface inspection is enhanced with visual aids or chalk indicators to reveal high spots. These interventions improve results, but diverge from strictly period-accurate methods, hinting at the procedural sophistication that might have been employed historically. Even with these modifications, fully matching the optical qualities, uniform reflectivity, sub-micron smoothness, and planar consistency, remains elusive. The tension becomes evident. If ancient surfaces were produced with only copper tools, quartz abrasives, and hand effort, experimental reconstructions struggle to reproduce the observed finishes at scale. Small-scale success is attainable, but the consistency, coherence, and mirror-like quality seen in artifacts and architectural elements often surpass what these reconstructions can achieve. Reproductions rarely maintain uniform flatness over multiple square meters, a hallmark of many Old Kingdom granite blocks. Microtopography remains subtly irregular, gloss is diminished, reflectivity is inconsistent. Yet the experiments are not failures in principle, they illuminate what is possible within known physical constraints. Coarse shaping and moderate smoothing are well within human capability. Fine polishing is possible in isolated areas given patience and careful control. The crucial limitation is scale, uniformity, and repeatability. Ancient artisans appear to have achieved levels of process control and labor organization that challenge assumptions about simple handwork. Measured roughness values underscore this point. Where data is available from archaeological artifacts, diorite statues of the 4th dynasty show Ra values estimated below 0.2 micrometers. Granite casing stones, where preserved, exhibit near-perfect optical flatness, with gaps between stones measured in fractions of a millimeter across spans exceeding 2 meters. Experimental reconstructions rarely achieve these metrics without significant improvisation or intensive iterative feedback, conditions difficult to reconcile with purely casual hand polishing. The implications extend beyond technical curiosity. The contrast between measurable surface quality and reconstructed capabilities highlights the nature of the contradiction. These surfaces carry a process signature. They are not merely smooth, they are coherent, uniform, and systematically refined. Each stone is a record of controlled material removal, incremental refinement, and spatial discipline. Their finish reflects not just labor, but structured methodology. Some researchers argue that repeated trial and error, combined with prolonged labor and cumulative knowledge passed across generations, could bridge the gap. Patterns of apprenticeship, institutional oversight, and ritualized workflow may have allowed teams to incrementally develop finishing techniques. The evidence of uniform quality across multiple artifacts and architectural elements supports the notion of standardized procedure. However, the experimental archaeology record reveals the practical limits of simple trial and error. Achieving consistent sub-micron surfaces over large areas is extraordinarily demanding, even with careful methodology. Thus, a crucial bifurcation emerges. If experimental reconstructions, even when optimized within period-accurate constraints, fall short of the observed surface quality, the contradiction deepens. Ancient artifacts appear measurably beyond what is demonstrably achievable using only the documented materials and hand methods. Conversely, if reconstructions successfully reproduce finishes that match Ra values, flatness, and gloss, then the perceived anomaly shifts. The accomplishment is still impressive, but the process becomes explainable through disciplined procedure rather than mystery. At this junction, we see the dual significance. One path emphasizes the limits of human effort against physical constraints, scale, material hardness, and abrasion physics. The other underscores the role of structured process, cumulative knowledge, and careful feedback in achieving outcomes that appear, even to modern measurement, extraordinary. Experimental archaeology does not yet definitively close the loop. It illuminates the space in which ancient engineers operated and the extreme demands of producing measurable surfaces that challenge assumptions about their technological capabilities. The next stage of inquiry moves naturally from this point. To compare measured ancient surfaces directly to modern engineering standards, analyze abrasion time across full architectural scales, and integrate labor, tool hardness, and surface physics into a comprehensive assessment. Only then can we confront the central question in full. What measurable engineering fact does not align with the assumed technological capacity? And what does this reveal about the ingenuity of those who shaped stone thousands of years ago? When we stand before a perfectly polished diorite statue or a gleaming granite sarcophagus, it is easy to marvel at the surface without realizing what it actually represents. The shimmer of reflected light, the precise fit against neighboring stones, the uniformity of flat planes, these are not merely aesthetic choices, they are the fingerprints of process. Every subtle reflection and every micro-flat plane embodies an unspoken methodology, a sequence of decisions and corrections repeated until the stone itself attains the desired geometry and finish. Surface finish is not decoration, it is documentation. To understand what this implies, we must step back and think in terms of process, not tools. The artifact itself records a history of sequential action. Each stage of abrasion, coarse grinding, medium smoothing, fine polishing, leaves a distinct signature. Coarse abrasives remove large imperfections and define geometry, but they leave deep scratches. Finer abrasives remove those scratches, but their effectiveness depends entirely on the uniformity of prior work. One cannot polish a high spot effectively unless it has first been reduced in height. Each stage, therefore, depends on the completion and verification of the previous stage. This is sequential control in its purest form. Sequential grit progression implies more than simply switching from coarse to fine. It requires knowledge of particle size effects, control over abrasive distribution, and understanding of material response. Experiments in modern lapidary reveal that skipping intermediate steps often results in residual scratches or uneven sheen, forcing repeated work or even partial reversion to coarser abrasion. For ancient craftsmen to achieve uniform mirror-like surfaces on granite or diorite, they would have needed an intuitive or explicit understanding of this hierarchy. Each abrasive has a role, and each must be applied with sufficient duration, pressure, and coverage to prepare the surface for the next finer stage. Surface inspection is the second layer of sophistication. Polishing is inherently subtractive. Material is removed continuously. Without periodic inspection, it is impossible to know whether one has achieved uniformity across a complex surface. Archaeological evidence suggests that some ancient objects were inspected using visual comparison, hand touch, and fitting tests. For example, multi-block constructions where stone faces meet with gaps under a millimeter imply that workers continually evaluated flatness during the finishing process. It is one thing to grind a single slab, it is another to coordinate the surfaces of multiple blocks to ensure a seamless fit. Inspection is not passive, it is iterative. It provides feedback to adjust force, motion, and abrasive composition. Without such feedback, uniform planarity and smoothness would be impossible at scale. Planarity awareness is intimately tied to inspection. Flatness is not guaranteed by random rubbing, it emerges from disciplined directional abrasion. Straight lines must be checked, high spots removed, low spots built up conceptually through successive passes. Experimental archaeology demonstrates that even skilled workers tend to introduce subtle warping if they lack a reference. Ancient monuments, by contrast, show planar coherence that is remarkable given the tools employed. Surfaces several meters long exhibit deviations of less than a millimeter. Achieving this requires intentional maintenance of plane geometry, likely through repeated measurement and adjustment, though the instruments may have been as simple as a straight edge, plumb line, or chord. The process is inherently geometric. Smoothness alone is not sufficient unless it is applied across a surface that is systematically leveled. Feedback loops are the invisible scaffold of all this work. Each pass of abrasive informs the next. Observation of scratches, reflectivity, and flatness feeds into adjustments in pressure, motion, and grit selection. Ancient craftsmen would have needed to respond dynamically, correcting errors as they emerged. Such loops are evident in the micro-topography of surviving artifacts. There are no residual grooves indicating neglected stages. The finish is coherent, suggesting that workers monitored outcomes continuously rather than relying on a single, undirected polishing pass. Feedback is also temporal. Repeated application over days or weeks allows cumulative improvement, slowly erasing imperfections introduced at every prior stage. Error correction is inseparable from feedback. Surface imperfections, minor pits, scratches, or unevenness cannot be ignored. They propagate through subsequent stages, potentially undermining smoothness or planarity. Correcting these errors requires recognition, selective material removal, and sometimes return to coarser abrasives to reset the surface before fine polishing can continue. Such iterative correction is labor-intensive and demonstrates not merely effort, but process discipline. Archaeological diorite and granite surfaces reflect this care. No artifact shows random scratch patterns indicative of haphazard abrasion. Each surface is a record of controlled corrective action. Smoothness, then, is not simply a goal, it is evidence. It is a tangible proxy for process sophistication. The finer the polish, the more stages were required, the more uniform the flatness, the more rigorous the inspection. The broader the surface area finished consistently, the more robust the labor organization and workflow control. These are measurable outcomes. Raw values, flatness deviations, and gloss units are not aesthetic abstractions. They quantify the fidelity of the process. The artifacts themselves preserve the metrics of engineering discipline. Experimental reconstructions underscore this point. When researchers attempt to replicate high-quality finishes without systematic grit progression, repeated inspection, and iterative correction, surfaces fall short of the ancient standards. Scratches persist, gloss is uneven, and planar coherence diminishes. Only when sequences are meticulously applied, feedback is actively monitored, and adjustments are made iteratively do test surfaces begin to approach the measured smoothness of historical examples. The implication is clear. Process sophistication is embedded in the finish itself. Yet we encounter a further tension. While individual artifacts, statues, small blocks, demonstrate this process signature, large architectural surfaces amplify the challenge. Multi-meter granite floors or sarcophagus interiors demand not only technique but coordination, workflow management, and logistical support. Maintaining consistent planarity, pressure, and abrasive quality across such expanses suggests an understanding of process that is both procedural and organizational. Surface finish at scale implies institutional knowledge. It is one thing for a single craftsman to perfect a small object. It is another for teams to deliver uniform quality across an entire monument or complex. In sum, the evidence from surface finish alone speaks volumes. Each polished plane, each reflective face, each tightly fitted block carries a hidden record of action. Sequential refinement, inspection, planar awareness, iterative feedback, and error correction. These are not abstractions. They are measurable, physical traces of process sophistication. The artifact embodies methodology as much as material. To observe the surface is to read the procedural intelligence of its makers. What remains is the critical question: do we find corroborating evidence in the archaeological record that such systematic process chains were actually applied? Are there traces of grit sorting, evidence of staged polishing areas, or inscriptions hinting at workflow control? If such evidence exists, it reinforces that the finishes are the outcome of deliberate, disciplined methodology. If it does not, the contradiction persists. Surfaces that behave like the product of a complex, sequential workflow appear in the absence of documented process. The surface finish, in essence, is both reward and riddle. It is the tangible confirmation that someone, somewhere, applied disciplined methodology to extraordinarily hard stone. It is also the measurable fact that continues to challenge assumptions. Achieving uniform submicron smoothness and planar consistency across artifacts and architectural elements is not merely a question of labor, but of sustained, disciplined, and likely institutionalized process. We now approach the next phase of inquiry, examining the archaeological record itself for signs of that process chain, seeking the traces of sequential abrasives, inspection protocols, and workflow organization that would validate the sophistication implied by the finish. Only by aligning surface evidence with material culture and site organization can we move closer to resolving the enduring tension between measured achievement and assumed capability. Archaeology often offers tantalizing glimpses of the machinery behind monumental achievement, yet in the case of high-finish stonework, the evidence is surprisingly sparse. Excavations around Old Kingdom quarries, workshop sites, and temple complexes yield copper chisels, stone hammers, dolerite pounders, and fragments of abrasive materials. Yet these remains, though invaluable, tell only part of the story. They document the tools employed, but rarely the sequence, intensity, or duration of their use. The artifacts themselves are silent on the subtle refinements, the iterative passes, the feedback and correction loops that the surfaces imply. Copper chisels, for example, are abundant. They appear in small numbers at quarries, in workshops, and even in some tomb contexts. Their hardness is known: soft, yielding, unable to scratch granite or diorite on its own. Their presence confirms that artisans possessed the basic implement, but not how they overcame the immense hardness of the stone. Quartz sand and other mineral abrasives are sometimes recovered in layers within quarries or near finishing areas. Fragments of coarse, medium, and fine grains survive, offering some indication of staged material use. Yet the evidence is fragmentary. We lack complete sets of sequential abrasives clearly labeled or organized. No inscriptions systematically detail how to progress from coarse to fine particles, or how to monitor the evolution of scratch depth and surface flatness. Workshop remains tell a partial tale. Grinding basins, work platforms, and partially shaped blocks suggest zones where shaping and preliminary finishing took place. Broken stones and chips of diorite, granite, and basalt accumulate in heaps, representing discarded material and offcuts. These refuse deposits, sometimes immense, are the closest thing to a production diary. They hint at an organized flow: rough shaping first, gradual refinement second. Yet the spatial footprint of these workshops is small relative to the scale of monuments they ultimately produced. For massive casing stones, columns, or sarcophagi, one would expect a proportional infrastructure: multiple grinding floors, dedicated polishing pits, water management systems for slurry, and storage for graded abrasives. The archaeological footprint is limited. While the evidence confirms activity, it is silent on whether these sites supported continuous, large-scale, and high-fidelity finishing operations. Production debris adds nuance but not clarity. Chips and fragments provide insight into tool-material interaction. They reveal the direction of strikes, the distribution of force, and the nature of material removal. In diorite workshops, dolerite pounders left crescent-shaped impact scars. In granite quarries, copper chisels combined with quartz slurry created tiny, polished chip marks. These traces document some mechanics of abrasion, but debris cannot quantify labor hours, track sequential stages, or reveal inspection protocols. It is a static record of dynamic processes. The lack of organized abrasive sets, standardized polishing aids, or durable templates leaves a gap between inferred technique and directly observed method. This gap is particularly striking when we consider the surface quality achieved. Artifacts demonstrate sub-micron smoothness, high reflectivity, and planar coherence. Surface finish is measurable, reproducible, and persistent across multiple monuments and centuries. Yet the archaeological record offers almost no explicit production manual to accompany these achievements. No evidence of standardized copperplate jigs, multi-stage polishing tables, or graded abrasive repositories has been definitively identified, nor do we find inscriptions describing process sequences, pressure application, or inspection techniques. We are left with finished stone as the primary documentation. The contrast between output and footprint raises questions. Were the methods so simple, so intuitive, that minimal infrastructure sufficed? Or is the archaeological record incomplete, obscured by time, reuse, or the perishable nature of auxiliary tools and temporary installations? Perhaps wooden guides, leather pads, or woven carrying frames facilitated finishing and inspection, but left no trace. Perhaps abrasive preparation occurred in dispersed locations, leaving few concentrated archaeological markers. Yet simplicity alone does not resolve the paradox. Even the most disciplined hand-polishing methods require careful coordination, sequential grit progression, pressure management, and continuous feedback. Small footprints suggest either highly efficient processes with minimal material evidence, or processes that were labor-intensive but ingeniously low impact in terms of archaeological trace. The measured surface quality implies systematic method, yet the surviving material record does not clearly reflect such organization. This tension is the documentation gap. The measured surfaces imply advanced procedural control, yet the physical remains of workshops, tools, and abrasives tell only part of the story. There is enough evidence to confirm activity and basic technique, but too little to map the full sequence or confirm the operational sophistication suggested by the finished stone. The contradiction is stark. Surface finish speaks to a high-order, repeatable method. The archaeological footprint remains almost silent on the details of that method. Was the apparent efficiency and high quality achieved through ingenious minimalism, leaving behind only the essentials? Or were we looking at a broader, more organized and now largely invisible industrial process, carefully tuned to produce results that exceed what surviving material suggests? The answer may lie in how we integrate surface analysis, labor modeling, and experimental replication, bridging what is measured with what is archaeologically visible. If the footprint is small, then perhaps the methodology was remarkably simple, yet extraordinarily disciplined. Yet if surface quality consistently exceeds what simple labor models predict, the contradiction deepens. The output is disproportionately sophisticated compared to the evidence of process. This tension sets the stage for evaluating the final implication, whether the method's elegance lies in minimalism or in unseen procedural mastery. What are your thoughts about this? There is a persistent assumption in both scholarship and popular imagination that simple tools can produce only simple results. A copper chisel, a slab of quartz sand, and human muscle, the story goes, can achieve nothing beyond rough shaping. Yet as we have repeatedly observed, the output, the diorite statues, the granite sarcophagi, the polished basalt floors, tells a different story. The surfaces themselves speak of intentionality, measurement, and refinement. The contradiction is not in the tools, it is in the system of use. Simple implements applied with deliberate process can produce outcomes that appear astonishingly sophisticated. To appreciate this, consider analogies in later pre-industrial craft. Telescope mirrors from the 18th and 19th centuries were hand-ground, polished using nothing more than abrasives, wooden tools, and patient repetition. Craftsmen worked over months or years to produce surfaces with sub-micron smoothness, planar accuracy, and precise curvature. No electricity, no diamond-tipped instruments, no mechanized feedback loops, just hand pressure, slurry, and iterative evaluation. The mirrors achieved optical performance that astonished scientists and enabled new discoveries of distant planets and nebulae. Here, the apparent simplicity of the tools belied the sophistication of the method. The process demanded discipline, sequential refinement, inspection, and error correction, precisely the qualities implied by the surfaces we see in ancient stonework. Pre-industrial lens grinding presents a parallel. Artisans in Europe and Asia, working with relatively soft optical glass, produced lenses capable of resolving fine detail, yet they lacked any mechanical lathes or modern metrology. Success depended on disciplined repetition, careful material preparation, and an acute understanding of how abrasives interact with the surface. Each stage was informed by observation. The artisan felt high spots, observed reflection, and adjusted pressure and direction accordingly. Small adjustments accumulated over weeks, producing a surface that met rigorous optical standards. Again, simple tools were sufficient, but only because the system in which they were applied was carefully managed. Returning to granite and diorite, the same principle applies. Copper tools and quartz abrasives are, in isolation, incapable of scratching hard stone to sub-micron finish. But the system, the iterative method, sequential grit selection, monitoring, feedback, and adjustment, amplifies the effectiveness of these tools dramatically. One can remove material at micrometer scales using simple implements if the operator understands the interaction between pressure, motion, abrasive particle size, and time. The system transforms the tools. The result is that a simple instrument, wielded with discipline, can generate surfaces that appear technologically advanced, even to modern eyes. This reframing challenges the assumption that sophistication requires advanced machinery. Ancient stonework does not necessarily imply unknown technology, hidden machines, or lost techniques beyond the period's material culture. It does, however, imply a form of organizational and procedural intelligence that is often underestimated. Here, sophistication is not measured in watts or horsepower, but in sequences, feedback loops, quality control, and human oversight. It is a cognitive sophistication embedded in practice, visible in the surfaces themselves, yet largely invisible in the archaeological record. Experimental reconstructions reinforce this point. When skilled modern artisans attempt to reproduce diorite or basalt finishes with hand tools and measured abrasives, success depends on adherence to method. A single misapplied pass, uneven pressure, or skipped grit stage compromises the outcome. Only consistent, disciplined application produces results approximating ancient surfaces. This mirrors historical examples. High-quality, pre-industrial optical elements or hand-polished marble floors required procedural control more than advanced tools. The lesson is clear. Tool simplicity does not constrain potential. Method sophistication expands it. Yet this reframing introduces a new dimension of inquiry. If simple tools can produce extraordinary finishes given disciplined process, then the question of contradiction shifts. It is no longer primarily technological, it becomes organizational. How were tasks sequenced? How were labor and skill distributed? How was quality maintained across multiple artisans, shifts, and locations? Producing a single polished surface on a diorite statuette is one matter. Producing uniform surfaces across a sarcophagus interior, a series of columns or large basalt pavements is another entirely. The sophistication we measure is as much about human coordination as it is about abrasive physics. Consider the implications of scale. Large architectural elements demand multi-operator coordination. Pressure and motion must be consistent across surfaces. Abrasive supply must be managed. Time must be sequenced carefully to prevent fatigue-induced error. Inspection protocols must detect deviations early. These are the same challenges faced by pre-industrial mirror makers and lens grinders, yet magnified across meters of stone rather than centimeters of glass. Here, the contradiction is not a deficit in material capability, but in human organization and process control. The ancient workforce had to function as a distributed adaptive system, translating simple tools into complex outcomes through discipline and coordination. It is in this light that we must reinterpret the measurable anomaly. The high smoothness, reflectivity, and planar consistency of diorite and granite surfaces are not necessarily impossible. They are, however, indicative of a level of procedural and organizational sophistication that exceeds what casual assumptions about primitive tools might suggest. The achievement is less a question of exotic technology and more a question of human ingenuity. How simple implements, applied with disciplined method, can yield surfaces that rival modern engineering expectations. The reframe also clarifies the limits of experimental archaeology. Attempts to replicate finishes often fail, not because the basic physics is unachievable, but because the distributed human system, the organization of labor, the continuity of method, the calibration of feedback, is difficult to reproduce outside the cultural context in which it originally existed. Modern experiments are isolated, performed by small teams, and limited in duration. Ancient projects may have employed structured oversight, institutionalized apprenticeship, and iterative refinement over years, creating conditions in which simple tools achieved extraordinary outcomes. Thus, the apparent contradiction, the mismatch between observed surface quality and assumed technological capability, may be less about physical limits and more about organizational imagination. The sophistication is encoded in procedure. The discipline of application, the sequence of operations, the attentiveness to measurement and correction, and the scaling of human effort to architectural scope. Simple tools become vehicles for complex outcomes, not through hidden machines, but through method, patience, and coordinated labor. We are left with the essential tension. The surfaces themselves are evidence of extraordinary discipline, yet the archaeological footprint offers only fragments of the supporting organization. The contradiction is no longer solely about how copper and quartz could remove diorite. It is about how human systems were structured to produce repeatable, measurable excellence across multiple artifacts and monuments. The question now shifts decisively. Is what we observe the product of technological limitation stretched to its extreme, or of organizational mastery applied with relentless discipline? Resolving this distinction will determine whether the engineering anomaly is a question of material capability or human process, and will guide our next inquiry into how evidence of that process might be traced within the surviving archaeological record. Ancient stonework is often framed as a contest between material and tool, as if the physical hardness of diorite or granite defines the limits of achievement. Yet closer inspection suggests a different story. The true sophistication lies not in the implements themselves, but in the humans who wielded them and the structures that organized their effort. The surfaces we admire, mirror-like planes, uniform flatness, coherent reflectivity, are the product of distributed intelligence applied over time, a choreography of labor, observation, and feedback. Labor organization emerges immediately as a critical factor. Experimental reconstructions demonstrate that producing submicron surface finishes on even small artifacts is labor-intensive. Now scale that to multi-ton sarcophagi, massive basalt floors, or granite columns several meters in length. One worker cannot achieve uniform planarity or consistent gloss over such dimensions. The workforce must have been structured, with tasks allocated according to skill, physical endurance, and sequential requirement. Coarse grinding could be performed by less experienced workers under supervision. Fine polishing demanded the most skilled hands, guided by continuous inspection. Labor, in this sense, becomes a system, distributed, hierarchical, and adaptive. Skill specialization reinforces this insight. Archaeological evidence suggests that some stone types, diorite in particular, were reserved for the most important statues or ceremonial objects. The care and precision in these surfaces implies practitioners who had mastered the subtleties of abrasive behavior, pressure control, and sequential refinement. Unlike modern craft apprentices, whose training may last years, these artisans were likely immersed in a culture where stone finishing was a central, lifelong occupation. Expertise was cumulative. One generation refined the techniques and passed them to the next, each iteration learning from the successes and errors of their predecessors. Generational iteration introduces a temporal dimension to the human factor. Surfaces are not just snapshots of labor, they are the endpoint of centuries of iterative refinement. Techniques honed over decades, perhaps even centuries, accumulate efficiency, insight, and methodical discipline. The high level of uniformity seen across multiple monuments of a single period suggests shared knowledge within an institution or guild, rather than isolated genius. Minor improvements, learned over successive projects, compound over time, producing measurable advances in surface smoothness and planar coherence. This may explain why certain Old Kingdom granite surfaces appear ahead of their time in quality. The sophistication was procedural, evolved over generations. Institutional knowledge amplifies the impact of individual skill. Workflows for producing highly polished stone surfaces likely involved explicit stages, checkpoints, and feedback loops. Supervisors could evaluate progress, redistribute labor to problem areas, and enforce consistency. Even if we find little direct archaeological evidence of such institutional scaffolding, no surviving jigs, templates, or written manuals, the end product embodies its presence. Submicron smoothness and coherent reflection across meters of stone cannot emerge from casual, uncoordinated work. The finished surface preserves the footprint of an organized, disciplined human system. This perspective reframes the apparent anomaly. The contradiction is no longer framed as how could they polish diorite with copper? It becomes a question of human coordination. How could small, simple implements wielded across a distributed workforce produce surfaces measurable against modern engineering standards? When we examine labor as an organized, iterative, skill-based system, the task becomes plausible. Simple tools, applied with cumulative knowledge, become instruments of extraordinary outcome. The anomaly shifts from the realm of physical impossibility to one of human process. Yet the feeling of anomaly persists, and this is where the human factor introduces a paradox of perception. Even recognizing labor organization, skill specialization, and generational refinement does not fully resolve the tension. The measured surface quality, the uniform submicron smoothness, optical reflectivity, and planar coherence, remains extraordinary. Modern engineers, with mechanized tools and precise measurement instruments, achieve similar results under controlled laboratory conditions. That ancient artisans could do so with copper, quartz, and hand pressure seems almost inconceivable. This is not a failure of logic. It is a recognition of human ingenuity operating at its extreme. The tension is heightened by scale. A single artisan working a 20-centimeter test block is one thing. Multiple teams coordinating to polish sarcophagi, columns, and floors simultaneously, ensuring consistency across blocks, is another. Every added square meter introduces potential deviation, uneven pressure, inconsistent abrasive grading, fatigue, or misalignment. That multiple monuments maintain uniform surface quality suggests an extraordinary level of workflow control, passed from person to person, generation to generation. It is process sophistication encoded in human behavior rather than hardware. Finally, we must consider error correction as a human function. Each surface imperfection, whether a high spot, micro pit, or subtle warp, requires judgment, recognition, and correction. Copper tools and abrasive sand cannot detect or respond to errors autonomously. Humans are the sensors and actuators, continuously monitoring, adjusting, and refining. The surfaces we measure today are the cumulative output of thousands of micro-decisions, each shaping the stone toward an optically and geometrically coherent final state. This is the essence of the human factor, the sophistication of the workflow itself. And yet, even understanding the labor, skill, and institutional knowledge, the surfaces continue to provoke awe. The feeling of anomaly persists because the achievement exceeds intuitive expectations. When we try to imagine reproducing submicron flatness across multiple meters of granite or diorite using only hand tools, the task appears almost superhuman, and yet the measured evidence confirms it was done. The human factor is the bridge between plausible mechanics and extraordinary outcome, an organized, disciplined generational system translating simple tools into engineering excellence. If the sophistication resides in workflow, coordination, and procedural discipline rather than in exotic technology, then the anomaly shifts. It is no longer a technological impossibility, but a social and organizational marvel. The next question naturally emerges: can we model that workflow, quantify labor distribution, and reconcile measured finish with plausible human organization? Understanding this will determine whether the contradiction is a question of technique, of human management, or of both intertwined in an extraordinary synthesis. The surfaces remain silent yet eloquent, recording the human factor in stone, the interplay of skill, coordination, feedback, and generational iteration. They remind us that engineering achievement is not measured solely in tools or materials, but in the systems and humans that apply them. And yet, even with this understanding, the measured perfection continues to astonish. Why does it still feel anomalous? That is the question we carry forward. To confront the contradiction directly, we must return to the numbers. The surfaces of diorite statues, granite sarcophagi, and basalt pavements are not simply smooth to the touch. They are measurable, quantifiable, and astonishingly consistent. profilometry and gloss measurements, applied to surviving artifacts and high-fidelity casts, provide a window into the exact demands of ancient polishing. Ra values, the standard measure of surface roughness, often fall below 0.2 micrometers on the finest planes. By comparison, industrial polished granite slabs intended for architectural use typically require Ra values between 0.2 and 0.3 micrometers to achieve comparable visual reflectivity. Optical quality surfaces, such as telescope mirrors or precision lenses, target even tighter tolerances, often below 0.1 micrometers. The ancient examples in terms of micro-smoothness occupy a range strikingly close to modern industrial benchmarks. Achieving such values requires more than casual abrasion. Modern techniques rely on sequential grit progression, often beginning with coarse diamond abrasives in the 200 to 400 micrometer range, stepping down through progressively finer grades and ending with ultra-fine abrasives exceeding 12,000 grit. Each stage removes scratches left by the previous stage while gradually reducing surface waviness. Hand-applied pressure, precise control of motion, and careful inspection accompany every pass. The time investment is significant. Polishing a small granite slab to Ra, less than or equal to 0.2 micrometers, may consume tens of hours for a single skilled operator. Scaling to multiple square meters multiplies labor exponentially. Experimental archaeology allows us to quantify the mismatch between what is achievable with period-accurate tools and the measured artifact surfaces. Using copper tools and quartz abrasives, a small diorite block can approach Ra approximately 1 to 2 micrometers with concentrated effort. Even with optimized motion, careful pressure, and fine abrasive preparation, further refinement towards 0.2 micrometers is extraordinarily slow and often inconsistent. Time models indicate that achieving a mirror-like finish on a multi-meter sarcophagus or granite slab would require thousands of human hours if only hand-applied pressure and period abrasives were used. In contrast, the archaeological evidence shows multiple massive surfaces finished to near optical smoothness, often within what must have been a practical construction time frame. The mismatch becomes apparent when we compare measured output with modeled effort. Surface roughness is quantifiable, so we can ask, if a single artisan works 8 hours a day with hand tools, what Ra value can realistically be achieved over a standard surface? For small surfaces, controlled experiments suggest that achieving Ra less than or equal to 0.5 micrometers is feasible after several days. Reaching Ra less than or equal to 0.2 micrometers on an entire sarcophagus or column face, however, exceeds the modeled effort by an order of magnitude. It is not impossible in principle, but it is labor-intensive to the extreme. Multiple artisans, extended timelines, and rigorous coordination are required. Beyond micro-roughness, planarity compounds the challenge. A flatness deviation of less than a millimeter over multiple meters, observed in granite casing stones and temple platforms, is striking. Simple random abrasion cannot achieve this. The process requires controlled directional movement, iterative correction, and continuous inspection. Modeling error accumulation under hand polishing assumptions shows that even minor deviations in force, motion, or grit uniformity propagate into measurable planar distortion. The surfaces we measure are too coherent to have emerged purely from unsupervised abrasion. We can also quantify reflectivity using gloss meters. High gloss units correlate with sub-micron smoothness and minimal micro-undulations. Artifacts exhibit consistent reflectivity across multiple facets, indicating that microtopography is uniform and directional. Experimental attempts using copper and sand produce uneven gloss. High spots reflect more, low spots less, and scratches scatter light diffusely. This discrepancy underscores the measurable gap. The surfaces behave optically, as if produced with modern high-grit abrasives, yet archaeological tools suggest a different capability. Grit sequencing adds another dimension. Modern polishing involves a deliberate progression, coarse to medium to fine, often with multiple sub-stages. In experimental archaeology, skipping or compressing stages leads to residual scratches or inconsistent optical behavior. Archaeological surfaces show no evidence of these intermediate scratches. The optical coherence suggests a refined, deliberate sequence. Here, the delta is procedural rather than purely mechanical. The method required not just labor, but controlled sequences maintained consistently across surfaces and artisans. Time estimates complete the quantification. For a multi-meter diorite sarcophagus, achieving Ra less than or equal to 0.2 micrometers with period tools could theoretically require thousands of human hours per surface. When multiplied by multiple elements in a single monument, the labor demand becomes enormous. If we accept that construction proceeded on realistic schedules, this raises the question: was the apparent sophistication a result of extremely disciplined organization, optimized workflow, and generational skill accumulation rather than mere brute force effort? The delta, the measurable gap, therefore emerges in three areas: achievable micro-roughness per unit labor, optical coherence across a surface, and planar consistency over scale. Each of these metrics can be quantified. For individual surfaces, hand-applied methods fall short of archaeological values. For large architectural surfaces, the shortfall is more pronounced. Yet when viewed through the lens of process, skill, and labor organization, the gap becomes an index of human ingenuity rather than proof of exotic technology. Finally, the confrontation forces us to ask a subtle question: is the contradiction real, or is it perceptual? In other words, is the measured gap evidence that ancient methods were physically insufficient, or does it reflect our underestimation of human discipline, coordination, and procedural knowledge? The surfaces themselves are incontrovertible: sub-micron smooth, planar, optically coherent. The methods, partially documented and partially inferred, appear insufficient in isolation. The reconciliation lies not in dismissing the measurements, but in recognizing that sophistication can emerge from organized simplicity. Before drawing conclusions, we must weigh both sides: the measurable engineering fact, the RA values, planar tolerances, and optical properties, versus the reconstructed capabilities with period-accurate tools. This comparison defines the contradiction. It is here, in this quantified delta, that the central question crystallizes. Did the ancient artisans rely on extraordinary organization and skill to achieve results that challenge our expectations, or is there a genuine mismatch between capability and output? This is the juncture where perception meets measurement, and where the final evaluation of the anomaly must begin. The surfaces of ancient diorite statues, granite sarcophagi, and basalt pavements confront us with a paradox that is both tangible and profound. They are at once familiar, stone polished by hand, and alien, in the sense that their measured smoothness, planar coherence, and optical reflectivity exceed what casual assumptions of ancient capability would predict. Yet as we have traced the evidence step by step, from roughness values to reflectivity, from flatness tolerances to labor organization, a clearer picture emerges. The mystery is not in the stone itself, nor in some hidden technology. It is in the discipline embedded within the process. We can now answer the central question directly. Does measurable surface finish exceed assumed technological capability? The answer is nuanced. On one level, the RA values, planar uniformity, and coherent optical behavior do appear remarkable when compared against the basic tools available: copper implements, dolerite pounders, quartz abrasives. Without modern diamonds or mechanized polishers, achieving RA less than or equal to 0.2 micrometers on granite seems almost inconceivable at first glance. Yet when we consider the totality of the workflow, the sequential grit progression, iterative inspection, error correction, and disciplined labor organization, it becomes clear that the capability resides not in exotic technology, but in human system design. The surface finish is a record of process intelligence written in stone. Each mirror-like plane, each high reflectivity face, each tightly fitted joint embodies knowledge that spans multiple scales. There is the microscale, where abrasives are selected, pressure is modulated, and scratches are gradually erased. There is the mesoscale, where flatness across single stones is maintained through iterative correction and inspection. There is the macroscale, where multiple stones, columns, and monuments must align, requiring coordination among teams, oversight, and standardized practices. This layered sophistication is measurable, and it is precisely what the stone records. Smoothness, then, is not magic. It is a quantitative signature of discipline. We have modeled labor, calculated abrasion time, compared grit sequences, and examined material hardness. We have observed experimental reconstructions and reviewed archaeological evidence. In every case, the same principle emerges. Extraordinary outcomes are possible when simple tools are applied within a highly disciplined system. Time, abrasion, feedback, and organization combine to produce results that appear technologically advanced, but are fully explainable within the limits of known materials and human ingenuity. The implications are profound. We have long equated tool sophistication with technological sophistication. A copper chisel, after all, seems primitive compared to a diamond wheel or a CNC polishing machine. Yet the surfaces before us demonstrate that the constraints imposed by primitive materials can be overcome by process intelligence. Human systems, coordinated labor, iterative refinement, multi-stage procedures can amplify the effectiveness of simple tools dramatically. The perceived technological gap diminishes when viewed through the lens of organization, feedback, and generational skill. This understanding transforms how we perceive ancient craftsmanship. Surface finish is not decorative flourish, it is documentation of method. The diorite statues, polished to mirror-like reflectivity, are not evidence of lost knowledge. They are evidence of disciplined knowledge applied over time. The massive granite sarcophagi, whose interior planes are consistent to millimeter precision, are not anomalies. They are records of workflow, labor coordination, and procedural control. Even the basalt pavements, which maintain coherent flatness across long stretches, reflect planning, measurement, and sustained attention. Each surface embodies a chain of decisions, a sequence of calibrated actions, and a culture of expertise that we can measure, model, and admire. Yet there is a haunting truth embedded in this realization. When we witness sub-millimeter precision across multi-ton stone surfaces achieved without industrial machinery, our assumptions about technological primitivity are challenged. It is not that the ancient world possessed machines we cannot identify. It is that we have underestimated the capacity of human systems to generate extraordinary precision using simple, accessible tools. What appears anomalous at first becomes an index of disciplined methodology, but it is still awe-inspiring in its execution. The paradox is resolved mathematically and physically, yet it leaves an enduring sense of wonder. Humans, not tools, created these surfaces, and they did so at a scale and consistency that rivals modern engineered finishes. This transformation extends beyond stone. If we can recognize that such procedural and organizational sophistication existed in stone finishing, it compels us to reconsider other domains of ancient accomplishment. What else might have been achieved through disciplined generational knowledge rather than advanced machinery? Monumental construction, metallurgy, water management, astronomical observation, each area may harbor measurable achievements that exceed our initial assumptions about capability. The lesson is not mysticism nor speculative technology, but a recalibration of what counts as possible when human intelligence is applied methodically over time. We are left, finally, with a new perspective on the past. The stone itself, polished to raw values approaching modern architectural standards, becomes a testament to human ingenuity. Smoothness is not a sign of magic, of lost technology, or of intervention from forces beyond comprehension. It is the record of method, practice, discipline, and organizational intelligence. Every micro-reflection, every planar surface, every optical coherence across meters of stone represents a cumulative achievement of labor, skill, and process management. The measurable contradiction dissolves when viewed in this light. The apparent impossibility was never in the stone, but in our underestimation of human capability. And yet, the closing question lingers. If such levels of process sophistication existed in stone finishing, hidden in the surfaces themselves, largely invisible in the archaeological record, then where else have we underestimated the past? What other disciplines, monuments, or artifacts bear the imprint of disciplined human organization that we have failed to quantify? What other achievements, measured and tangible, challenge the assumptions of technological capability imposed by tool appearance alone? The surfaces remain as silent teachers. They remind us that engineering, in its deepest sense, is not only about materials or machines. It is about process, method, feedback, and coordination. It is about the human factor magnified across generations, producing measurable results that confound expectation. And in that revelation lies the true transformation. The past is more sophisticated than we imagined, and the story of smoothness is the story of disciplined human intelligence writ large in stone. We step away from these surfaces not with answers about magic or mystery, but with a profound understanding. The ancient artisans did not defy physics. They mastered process. They understood the relationship between time, abrasion, observation, and correction. And in doing so, they left us a record that continues to challenge, inspire, and transform our perception of what primitive really means. The final reflection is this: the stone is disciplined, not mysterious. The finish is measurable, not miraculous. And the lesson is enduring. Wherever we see evidence of extreme precision without industrial tools, we must ask not what they lacked, but what processes, systems, and human ingenuity they applied, and consider in turn where else we may have underestimated the capability of the past. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.